10, 9, ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Greetings and salutations. Welcome back to the latest installment of Not So Sirius. Today we're going to talk about dark energy. To tackle this topic, we're going to cover a couple points. The first is we're going to talk about the history of dark energy. Then we're going to talk about the evidence that supports the existence of dark energy. Thirdly, we're going to talk about the nature of dark energy, so what it actually is and what it could be. And then lastly, we're going to talk about the implications of dark energy into the ultimate fate of the universe, so how the universe is going to end once we're long gone. But first, let's do the news.
The first news topic for this week is Comet Neowise. The Comet Neowise started to get bright earlier this July, and it's going to be about 30 degrees above the horizon in a few days. And also, when we're recording this today on July 22nd, it's making its closest approach to planet Earth. And depending on where you are and where you're listening from, it's probably best to look online and figure out what time of the day is best and what location to look at. With your naked eye, depending on what kind of eyesight you have, it's a bit blurry, and you're best to use either binoculars, or if you have access to a telescope. And basically you'll just see the coma being the front part of the comet, and then the giant tail streaking behind it. And it's in the northern sky, as I mentioned, and it tends to fall just below the Big Dipper.
And in another interesting piece of news, and a sick twist of fate from the universe, scientists have watched a black hole turn off its corona, but then it came back, so never mind. And so what that is, sorry, Michael?
It blinked.
Yes, the black hole's corona blinked, so it turned off for a year, which is a pretty long blink. But what it is essentially is the jet that comes out of a that is generated by black holes, which is called the corona, I believe, turned off. And the scientists are not exactly sure why that is yet, but it's thought that maybe a star got caught in the accretion disk, or maybe even the corona, and it disintegrated, and that would have led to the corona shutting off for a second or a year.
Mm-hmm. And then, as always, all the sources to these news articles can be found below in the description.
All right, so obviously today's topic is dark energy. But before we get into it, let's kind of define what dark energy is first, and also separate it from what we talked about last week, which is dark matter. First of all, dark energy it's also another theoretical concept, but it basically is just an explanation for the acceleration of the expansion of the universe. Last week we talked about dark matter, but I think for the context of this episode and the way we frame it, and just for people in general, like, there should be a separation, a distinction between the two. Dark matter pertains mostly to the rotational curves of galaxies and the known matter in the universe, whereas dark energy, like I said, again, is the idea of is an explanation for the acceleration of the expansion of the universe. And so they're similar in the ways that both things that us as scientists, or just scientists in general, like, don't know of and are postulating are there, but we observe them because we can see them from our research and things like this. So they're similar in the sense of what they are in terms of what we think, in terms of how we use them to explain certain things that we see, but they're different in the ways, and just in strictly the ways that they're observed.
Well, yeah, they explain different things.
Exactly. Yes.
Right. But before we can completely understand dark energy, we have to learn about the history of how it was first discovered and even theoretically predicted at first. So correct me if I'm wrong, but I believe it was Einstein that introduced dark energy at first, right?
Yeah. And so it was in the early 20th century. And there was Einstein and theoretical physicists, and also astronomers. Now, astronomy, or the field of astronomy, wasn't as refined, at least in terms of instrumentation, and not as advanced as physics was in predicting things in the universe. And so, for example, I think historically, the theorists in trying to understand the universe are always ahead of the observationalists or the experimentalists, just because the technology isn't as advanced yet. And so that was the case in the early 20th century with Einstein and astronomers. And so when astronomers looked out with their crude, archaic telescopes, at least compared to what we have today, they saw the universe as being static, unchanging. They saw the stars, and they didn't really consider a past universe or a future universe. Everything seemed to be unmoving and the same. And so when Einstein generated his theory of gravity, or his general theory of relativity, in it, he included something known as the cosmological constant, also known as the uppercase lambda, and our logo, Everything Astronomy. And so he added this to kind of justify what astronomers saw, and that was a static, unchanging universe. And so when he postulated the universe, he understood that there was a bunch of matter in the universe, and that this matter attracted itself, or another matter, so that he, in a sense, originally thought that the universe perhaps would be expanding, but all this matter would attract itself and collapse in on itself. But astronomers said otherwise, and he had to kind of come up with a way to explain his reasoning based off what astronomers observed. And so he added this kind of anti-gravity to add into his equations so that he could say that the universe wouldn't collapse in on itself, and that there's some other unknown force, or what he added in as a cosmological constant, to kind of explain this static universe. And it turns out, and then around like 1930, Hubble and a few other astronomers discovered the idea of the expanding universe. And so then Einstein kind of considered this cosmological constant his biggest blunder, because he added it in to explain that the universe was static. And then all of a sudden, about 15 years later or so, astronomers discovered that the universe was actually expanding, and that it was not static as once thought.
Yeah, and so, I mean, initially, when Einstein was creating general relativity, the thought was that, well, there was no evidence that the universe could be anything other than fully static, infinite in all directions. The idea, I don't even think the idea of the Big Bang had come up. And so, then gravity obviously is an attractive force, so things come together under gravity. And Einstein, but there was no evidence for the universe coming together. And so, as Michael was talking about, to balance this coming together out, to kind of justify what people were seeing, he added in this cosmological constant, which essentially kept the universe stable. There was a gravity pushing in, and then there was this thing that was keeping it out. And then when the expanding universe was discovered by Hubble and some others in the 30s, Einstein thought that this was his biggest blunder, not only because it didn't explain the expanding universe, but because the universe under this cosmological constant, or the explanation that Einstein gave for it, led to an unstable universe. So because it assumed that it assumed that there was always something to push out, but as we know, stuff is not evenly distributed in the universe, and so under his model, the universe would have been vastly unstable. And so again, this idea of the cosmological constant being just a constant outward pressure, where the empty spaces of the universe essentially act as negative masses of gravity, this idea didn't hold up anymore.
Mm-hmm. And then this idea of the cosmological constant, and Einstein's, as he called it, his biggest blunder, it really didn't come up again in astronomy until the late 1990s, around 1998, when astronomers were observing supernova, or more specifically type 1a supernova, which would be a white dwarf that's orbiting a larger star, and like the mass is kind of flowing off the larger star onto the white dwarf. The white dwarf gets too large, explodes in what's known as a supernova. And astronomers were observing this, and they discovered through this that the universe was actually accelerating. And so to explain the acceleration of the universe, then astronomers kind of revisited, and physicists revisited the idea of the cosmological constant, and introduced more formally the idea of dark energy.
And so, again, to clarify, what the type 1a supernova, I believe, correct me if I'm wrong, they have a very constant brightness.
They're often called standard candles.
Yeah, and so they're called standard candles, and essentially, because they're of a constant brightness, we can estimate how far away they are based on how much light from them is coming to us. So if I hold out this quote unquote standard candle a meter away from me, it's pretty bright. But if I put it 100 meters away from me, it starts to become pretty dim.
Right.
In the same way, we can use the type 1a supernovae to know how far away they are.
Mm-hmm.
And
yeah,
through that, we notice that things further away from us seem to be moving away from us quicker. So if again with the candle analogy, if I hold a candle away, if I hold a candle 1 meter away from me, it would be moving away from me slowly. And if it's 100 meters away from me, it would be moving away very, very fast. Right. And from that, we started thinking that must mean that space-time or space is physically expanding, and that would make sense. So if we assume that space was expanding at a constant rate, the further away things are, the more space there is between me and it, and therefore the faster it would be moving away from me.
Mm-hmm. And this was all proven given the fact that as soon as a white dwarf hits a certain amount of mass, it explodes, and so every single time it explodes with the same amount of energy. That's why it's called a standard candle. But the way that we're able to tell that that type 1a supernovae that are further away are moving faster is through, we mentioned it before, through a Doppler shift or a redshift. So essentially, as light in the solar system and the universe moves away from us, the more less energetic that it gets on the electromagnetic spectrum. That's why, as you may know, that red is the least energetic amount of light, and that's why it's called a redshift, as it decreases in the amount of energy and increases in wavelength. And so we're able to, because we know how much energy and how much light comes off of these supernovae, we're able to compare how far away it is and how fast it's moving based on how redshifted it is.
Yeah, and it's also, although it's called a standard candle, it may be best to call it a almost standard candle, because it's very difficult to determine the exact velocity outward of these supernova. And also it's difficult because not all white dwarfs are exactly the same, and they don't give off exactly the same energy, even though they all have the same mass limit, as Tommy referenced, of 1.4 solar masses. At that point, once they get any more massive than that, they explode in what's known as a type 1 supernova. And so at first, and when these two, I think two separate research groups, one being at Berkeley Lab out in California, when they first kind of collected all this data of different distant supernova, they only had a handful of supernova to work with, maybe less than 100. And since there's also a lot of dust in between us and these supernovae, so determining the exact brightnesses, determining the exact outward velocities of these exploding stars was very, very difficult at the time. And so there are large enough error bars where they thought it was accelerating, but and they're quite confident of it. But over the past 22 years since then, they've collected tons of more data on distant supernova to confirm and kind of shorten the error bars to confirm that it is in fact accelerating.
I also think it's important to recognize that, like, why this was so significant, this discovery in the 1990s of the type 1a supernova, is that up till now, like up to this point in history, like I think astronomers knew that the universe, like from Hubble, that the universe was expanding, right? But to them, it was like they thought that it was expanding, but it was slowing down. Expansion was slowing down, and that at some point we would hit a limit where the universe begin to collapse at a certain point, or gravity went over. And so I think astronomers theorized at that point, okay, so what extent, when will it slow down, and when will it stop? And it's like, how much is it slowing down? And so the fact that like they found this discovery in the 1990s with the type 1a supernova, that like they were wrong, in fact, like that the universe is actually speeding up in its expansion, was like crazy. Like, I think it was a pretty big deal at that point, because it kind of broke a lot of astronomers' views, or like just their ideas of how the universe was behaving.
Yeah.
Right.
It was a huge shift in our perspective.
Yeah.
Yeah. And that was in 1998, and that was the first time that the term dark energy had been coined. Just because prior to that, no one, most astronomers and physicists seem to be aware and know that the universe was expanding, but no one had really seen the expansion keep accelerating, and so there was just no need for this concept to exist. But in 1998, the term dark energy was coined, and the dark energy is the force, essentially, or the energy responsible for creating this acceleration in the rate of expansion of the universe.
And I know Joe mentioned it before we started recording, but ever since the 1998 discovery, scientists have continued to look at other places for evidence of dark energy, and that we were able to find proof in the cosmic microwave background.
I mean, so there was, I mean, we briefly touched on the history, which is not a very long and arduous history, I would say, even though it might have been. It doesn't seem like a very long history of dark energy, but there's sort of three big lines of evidence that we have that tell us that there is this dark energy, or there is a need for something to be explained. And the way that we currently explain it is through this dark energy, even though we have very little idea about what dark energy actually is, but we'll get into that later. So the three lines of evidence are, generally speaking, that the first one is that the universe seems to be flat. And so what that means is that essentially the very large, on very, very large scales, if you shone two lasers parallel, the beams would over enormous distances, the beams would never cross or diverge. They would just stay parallel.
Yeah, without outside interaction, that is.
Right, and that's what a
curvature
flat
to the universe.
Right.
Yeah,
no curvature.
It means that if you took a triangle, the sum of all of the interior angles would stay 180.
Right.
And so we have seemingly more mounting evidence that the universe seems to be flat or very nearly flat. And so for that to be the case, we need a form of dark energy dark energy has to exist. And so the universe seems to be flat, and we have some good evidence for it, including what they call anisotropies in the cosmic microwave background, which essentially show that the universe is close to flat, in the sense that by looking at the CMB and by looking at the anisotropies in the CMB, we can determine sort of the overall curvature of the universe, and it seems to be within a fork that contains flat. So it could be a little bit unflat in either direction, but the margin of error contains perfect flatness. And so that's the first line of evidence that tells us there is a form of dark energy and this thing exists.
Right, and I'd like to also touch on, there were some other different shapes of the universes that we'll touch on later, that determines how the universe will end. But there's also two major types of geometries that were also proposed. There was a closed universe, where essentially the universe is contained within itself and is non-infinite. And this would mean that if you were to take the fabric of the universe and draw a triangle, the sum of the angles inside the triangle would be greater than 180 degrees, which would signify that the shape of the universe would then be elliptic, so almost egg-shaped in a way. And that the other counterpart to that one is that there is an open universe. So if you were to draw triangles on that fabric, that the sum of those angles would be less than 180 degrees, which would signify a hyperbolic geometry and an almost infinite universe.
Yeah,
and so
hyperbolic meaning saddle shape.
Mm-hmm.
And so what that means in terms of the laser analogy is, in the closed universe, if you shone the two parallel lasers at some point, the beams would eventually cross over.
Yes.
And on the contrary, in the open universe, if you shone two parallel beams, they would diverge forever and ever and never see each other ever again.
Right.
And yeah, so the first line of evidence that supports dark energy is the seeming flatness of the universe, because for the universe to indeed be flat, we need dark energy to exist to keep it flat, because otherwise the force of the universe would take it to another shape.
Mm-hmm.
Yeah, and so like kind of to encapsulate everything, I think it's important to realize that like we can define things as flat because from what we observe up to the point, up till now with everything, it seems like the universe is flat. So the idea of there being a closed or open universe is just there for us to be able to kind of keep our boundaries in a sense, just in case we don't have all the evidence, because these are still in a sense theories that we're using evidence to prove more and more. But just in case the universe is not flat, we can understand that if it's not flat, then what way is it going? Is it closed or is it open?
Yeah, exactly. Like everything we found has pointed towards a flat universe, but that doesn't rule out either an open or a closed one as well.
Exactly.
And one of the really hard things with such huge, with finding evidence and precise numbers over such huge distances and so many things, is that it's very, very hard to get the exact number. For most of these things, we have a fork between which we think these constants and these numbers fall. But it's exceedingly hard to pin it down to the precise thing. And the biggest problem with the whole flat universe is that for the universe to be truly flat, the geometry of the universe needs to be there's this
parameter that defines the shape.
The parameter that that's it. The parameter that defines the shape of the universe needs to be exactly, I think it's 1.
Yeah, 1.
And the problem is that we have that parameter to within a fork that contains 1, but if it's even slightly not 1, or if it's slightly greater or slightly under, it means that the geometry of the universe changes. Right. And this is the biggest problem that we have in trying to pin this down, is that we need to get to within very small margins of error, which is very difficult.
Yeah, I think currently it's just under 0.5% margin of error, which is fairly good, but like Joe mentioned, we need to get it to exactly 1 to prove it's a flat universe. And so a 0.4% margin of error could mean that we're living in any of the 3 different types of universes based on the number we currently have.
And so we talked about the existence of 3 lines of evidence to support dark energy. The first one is this flatness of the universe business. And then the second one is the existence of large-scale wave patterns in the mass density of the universe. And so what that means is that on enormous distances, we're observing sort of wave patterns in where stuff is in the universe. So stuff seems to be existing in kind of waves.
Right.
And this would come from, I believe, the existence of very, very large sound waves in the early universe, which would have permeated out to kind of give us the mass or the stuff distribution in the universe as we have it now. And for that to exist, we need dark energy to be at play.
Yeah, so a way to visualize this isn't the one-to-one comparison, but a way to visualize this at home is if you have a cup of water or a body of water that you have, imagine your hand is dark energy, and if you just dipped your hand into the water, you would create ripples along the surface of the water, and those ripples would represent the areas of the universe that are more dense and contain more matter, whereas the valleys or the troughs have less dense and less matter. And so that's one way you can kind of envision it. Obviously, it's not exact, and it's on a much grander scale than just in a cup or in a lake, but that's one way you can visualize it.
And so essentially what these kind of waves have told us is that we can, and so with these waves, we can analyze the void, kind of the space between these waves, and they've provided evidence for, not only do they help us determine how far things are from us, which is useful, they also help us measure the rate of acceleration of things away from us. And that's a second line of evidence that confirms that the universe is not only expanding, it's expanding at an accelerating rate.
Right.
Which means, and I don't think we've really talked about this, that not only are things getting further away from us, they're going quicker and quicker. They're accelerating away from us at a non-constant rate.
Right. And so if you have, one marble 5 feet away from you, that's going away from you, and you have one marble 10 feet away from you that's going away from you, that means that the marble that's 10 feet away is going away faster and faster compared to the 5 foot away marble.
And so
also explain why, even though the universe is 13.8 or so billion years old, the diameter of the actual universe is 92 billion light years across, because at least in the observable universe, the outer reaches are expanding further, or accelerating in their expansion.
Yeah, and so the kind of two things. The first is that to build on the model of the marbles going away from us, we talked earlier about the fact that space itself is expanding. It's not that further away there's just more stuff. It's that everything between us and other stuff is getting bigger. And so, for example, that means that if I have a marble 1 meter away from me, it would be rolling at a certain speed. And if the marble were 2 meters away from me, it would be going twice as fast. And that would mean if the marble that's twice as far away is going twice as fast, that means a non-accelerating expansion. That's just the fixed speed, or the fixed speed increase. And whereas with the accelerating expansion, it means that the marble that's twice as far away from me is going more than twice the speed. And so that's the first point. The second thing I had to say, Michael, what did you just talk about?
I talked about the diameter of the universe.
Oh, right. The other thing is that the fact that the universe is expanding at an increasing speed, that kind of limits how far we can see, because we know that the speed of light is a certain number, and given that things far away from us are moving faster and faster, there is a point where they're moving away from us quicker than the speed of light. And that kind of place where they move away quicker than the speed of light from us is, I believe, from my understanding, the limit of our observable universe. And so there is quite possibly stuff that lives outside of the observable universe,
just
and
over our horizon.
Exactly, that's further than the horizon of what we can see. So that part of the universe can never be accessible to us.
And then things continue to get more and more beyond the horizon, until if you extrapolate into the far future, we may be the only galaxy that we can, or the stars in our galaxy are the only stars or galaxies we'll be able to see in our night sky. Until even those accelerate and expand away from us.
And so the third line of evidence. So the first one was the seeming flatness of the universe. The second is these large-scale wave patterns, and then the third, which is the third and I think biggest line of evidence, is that we can see things, and how far, and so we can see things, and more we know how far they are from us. And from the redshift, we can determine how fast they're moving away from us. And with a lot of, now thanks to computers and satellites and more measurements of these far things and how quickly they're moving away from us, we've been able to see and notice the pattern that the further away from us they are, not only are they going quicker, they're going quicker and quicker and quicker at an accelerating rate. And so that's the third and probably biggest line of evidence that tells us dark energy is a thing and it exists. And
so kind of getting into deeper, like moving on from the fact that it exists, we don't really know what it is still. It is still a theory in the sense that sure, we say that it exists because we can see the fact that the universe is expanding at an accelerating rate, but we don't know what it actually is. So I believe there are a few different ideas of what it could be that people theorize, and I think there are three popular theories that people tend to go with, or three possible.
Just before we get into that, all of our other measurements tell us that, well, all of the measurements that we have about our cosmos tells us that there's about 5% normal matter, roughly 30% dark matter, as we talked about last week. But then the remaining 60 some is of the mass that's needed for the universe to be as we see that it is, needs to come from, again, yet another source, and
called dark energy.
Dark energy, yeah.
Exactly. But like I said, we don't really know what this is, right? So I think, to my understanding, there are three popular theories what dark energy might be that people or scientists trying to like understand what it is. I think they're three. Am I right in saying there are three, or is it two?
Well,
Two?
two and another
Two and a half.
Two and a half.
Two like solid ones, and then maybe like a third one that is not so like theoretical
Right.
supported.
And then
So I believe like the first biggest one is the idea of quintessence, that deriving from what the Greeks thought. It comes from like a Greek word, I'm sure, but I believe the idea of it is that it's some fifth fundamental force that we don't really know that exists that causes this energy, dark energy push off, that causes accelerating expansion, I believe.
Yeah.
Mm-hmm.
And so basically, I think quintessence comes from, some Greek word that derived from some Greek word that refers to a fifth element. But in this case, maybe we're talking about a fifth fundamental force. And one issue with dark energy is when you're thinking of dark energy, you can think of, as we have talked, about the acceleration or the accelerated expansion of the universe. But you can also think of it like a kind of an anti-gravity. It's this repelling force that we're not exactly sure how it works. And so one idea is that dark energy, well, we know it like repels. We know that one characteristic trait of it is that it has something known as negative pressure. And so everything in its presence seems to be pushing away from each other. And so we have this idea with quintessence that it's a fifth fundamental force to say. And that's compared to another idea known as the cosmological constant. So there's different epochs in the history of the universe. And so after the Big Bang, about 13.8 billion years ago, radiation dominated, but also radiation, as the universe expanded, kind of diluted quite quickly, and it was overcome by matter. And so all of a sudden we entered a new epoch of the universe that was dominated by both baryonic matter, as we talked about last week, matter like you, us, and this planet, that we can that interacts with electromagnetic radiation, and also that includes dark matter. But that also gets diluted as the universe expands. And so then as that dilutes, and as radiation already diluted, then the universe, we at least believe, to become dominated by something known as dark energy. And so, and for at least the cosmological constant, it has the word constant in it, so meaning it's stationary over time. And so that suggests that as radiation and as matter got diluted, and it was only a matter of time before dark energy took hold and started the accelerated expansion of the universe started quite quickly. And so that happened, scientists believe, at least looking at data, happened between 5 and 7 billion years ago, when dark energy, whether that be constant with time or quintessence, meaning that it changes with time, dominated at this point.
And so we have these, well, there's to me, quintessence seems to be just a twist on this cosmological constant idea, in that the cosmological constant is just a way of explaining this negative pressure being just an intrinsic part of space. It just exists. It's everywhere. It's the same everywhere. This idea of quintessence would tell us that it's this negative pressure is created in varying amounts, depending on the place and time that we're in. And so essentially all we know is that what we figure this dark energy is just kind of this thing that's diluted, it's intrinsic, it's everywhere in just space. So if you think of I don't know, space as just being this mesh, it exists at every single part in that mesh. It's just a part of what space is. It's a part of what creates the separation between the atoms and the people and the planets and things like that.
And so when we talked about dark matter last week, we brought up the idea that it's likely to be a particle. That's not to be the case with dark energy. Whereas Joe said it's intrinsic. And maybe a good way to think about it is, we think of the fabric of space and time, but we can just think of it all in a body of water. So it's basically just this giant field that's constant over the entirety of the universe. Where the density, if it's constant, or the density is like the same everywhere you go.
It's kind of like air, if you think about it. Like it's just there in our space, right?
Yeah, it's just there. It does its thing. But the thing is, with the changes in the cosmological constant, depending on what theorists think, it can also change the big picture ending of our universe. I know this also correlates with what we talked about earlier with the geometries of the universe. But if the cosmological constant happens to be less than 1, then, or even equal to 1 in a flat or open universe, the results are the same. There's really 2 big options that can happen. One of them is called the Big Rip, and the other one is called the Big Freeze.
But it's not the cosmological constant, it's the omega value, right?
Yeah,
Yeah.
but
I believe it's the omega value.
they're correlated with each other, right?
They are related, yes.
Yeah.
I believe. Yeah. I think it's called omega lambda. It is omega sub lambda, which is omega. Yeah. They're related.
There's omega, which is composed of 3 omega values, meaning omega m for omega all of matter, so matter and dark matter. Then there's omega rel for relativistic, which is all relativistic particles, or just like neutrinos and other matter that's moving, like in photons that are moving very fast. And then there's omega
Lambda.
uppercase lambda, which is reference to dark matter. And then you add the 3 together to get your omega value. So that's the last digit in the Greek alphabet.
Mm-hmm.
And then what omega is it's a ratio between the density and then the critical density for either the universe to keep expanding or to collapse in on itself or to stay continuous or stay.
Yeah, and so we assign different values. If it's 1, we believe it's a flat universe.
Flat universe, yeah.
If it's greater than 1, it's a closed universe. If it's less than 1, it's an open universe. And so in general, loose terms boundaries for how we can see what our universe is.
I think there are 2 things again that I should mention. The first is that this whole omega business that we've been talking about and the flatness or the curvature of the universe, that comes from a model of what the universe could be, which is called the lambda CDM model. So it's it's not just some persons, but it is a way of thinking about how the universe behaves. There are other explanations out there, but the lambda CDM model, which is the one that contains this whole omega stuff that we've been talking about, seems to be the one that's correct, and it's the widely accepted description of how the universe works. The second thing that I should mention is that the reason why finding this dark energy is probably going to be so hard, and the reason why dark energy has proved to be so elusive to us is that it's not dense. And when I say not dense, it's really not dense at all.
Right.
So for dark energy, if dark energy really truly is just everywhere and is a part of space as we know it, and if it is indeed 68% of the mass energy in the universe, that means that the density of dark energy would be 10 to the minus 27 kilograms per cubic meter.
Yeah.
Extremely light.
And then, but the thing is that seems like it's not dense and it's not important, but added over the entirety of the universe, it adds up to a huge force. That's driving.
It's a huge.
It's one of the context of the size of the universe here, too.
Right.
Like, it's very light, but it makes up a lot, and so.
And then also that one thing we didn't mention before that you kind of remind me of, Joe, is one of the biggest problems with dark energy is not only figuring out what it is, but why there's 2 different predicted values of the cosmological constant. It's known as the cosmological constant problem, where, as you said, it's 10 to the negative 27 kilograms per, was it cubic meters. That's predicted by observations. But according to quantum field theory and theoretical approaches to dark energy, it should be far, far, far larger than that value. And so right now, that's a cutting edge research in the field where scientists are trying to figure out why there's this discrepancy between the 2. And perhaps the answer to dark energy lies in trying to figure out why there's that difference between the 2 solutions.
And the thing is, we're getting, lost and confused on what the values could be and how dense it is and, what the overall omega value is. But overall, it's one of the most important things in the universe, as it determines, A, the shape and size and geometry of the universe and how we understand everything at all. And then B, how the universe is even going to behave in the future, because if it's called the Big Rip, but if the acceleration continues past the speed of light, it's like we mentioned in the episode with black holes, where if gravity is too strong, you get spaghettified into a single line, 2-dimensional line of atoms. That could be what the future of the universe holds for us. The acceleration is so large in every single direction that you just get torn apart and atoms break apart and then there's nothing left.
I mean, so we have a couple different options for the ultimate fate of all of us in our universe. And so one of them is this big rip idea, in which things just keep getting further and further away from us. And so initially the Milky Way, our galaxy, kind of gets left alone, and everything else gets so far away from our Milky Way galaxy that we can't see that other stuff anymore, and we kind of become lonely. But then as time goes on, if time is infinite, which if time keeps on going forever, which this version of the end of our universe needs, then eventually our galaxy will itself just get way further apart, and it'll get diluted, and then we won't even be able to see the edges of it. And then ultimately further down the line, our planet will start to get really very lonely, and then ultimately everything within it is going to get super lonely. And that's the big rip. That's everything just being too far away from each other to interact.
But not to worry, because our planet Earth will be absorbed by the sun in 5 billion years. So
Right.
It's all in the broad strokes purpose of the end of the universe. So it's
end of the universe. We're talking
far
about
out from like our own life.
5 to the power of a billion years.
It's very far in the future, kind of.
Right.
You're right. But it's still important. It's still interesting to talk about.
Yeah. And so the big rip relies on the universe keeping on expanding at this still increasing rate.
It relies on the flat or open universes,
which is what I think what we're seeing now.
Mm-hmm.
But however, we know that it's possible as well that we go to this thing called the Big Crunch, where if this dark energy turns out not to act on sufficiently long distances, or if it dies out or something like that, then gravity could start to win over again. And then instead of keeping on growing, it'll slow. The rate at which it grows will slow. And then eventually it'll start coming all back in on itself. And then it'll collapse. And then maybe, or maybe not, that's what makes the Big Bang.
Yeah.
And we'll have another Big Bang. And then this other universe will be born from us.
Yeah, in a cyclical cycle. And I know the Big Crunch is one of the most popular theories, just because it's a simple explanation for what the Big Bang could have been. It's just the remnants of the universe before us. And I know that there's possibilities that we can use thermodynamics to detect what happened in the past universe before the Big Crunch happened. But the problem is, as we mentioned, our omega values correlate with the Big Rip, which happens in a flat or open universes. But the Big Crunch is only possible when the omega value is greater than 1, and that happens in a closed universe.
Which is a bummer, as you mentioned, because what we think is going to happen now is not it does not explain how the Big Bang happened. So that's another
Right.
slight issue right there. And then
There's a third one that is possible as well within open and flat universes called the Big Freeze. And essentially, I'm not entirely sure what the conditions for the Big Freeze are. It's also called the heat death of the universe, but essentially, the what?
Or the Big Chill.
Yeah, the Big Chill. But essentially,
it means it's cold.
Yeah, no. Essentially, before the Big Rip is possible, everything in the universe gets so far away from one another that the basic fundamental laws of thermodynamics won't allow any work to happen. So if you were to go to the gym and lift weights or push boxes or do whatever in your daily life, that's work. But without the fundamental laws of work, there can be no physical interactions with one another, and so everything would become completely static.
But you still have 0-point energy, or like at the quantum level.
I think it's called no thermodynamic free energy. So there's no more energy to work, and so that would happen before the Big Chill would happen before the Big Rip is possible.
Yes.
Yeah. So if you didn't want to be a single line, 2D line of atom, you'll be frozen. So
you won't even know.
Which is great.
Stay tuned for the future of the universe.
Yeah. I mean, obviously these are all still theories, and these are all timelines of things that we will probably, we'll never be able to see, I believe, unless somehow we invent time travel and someone in their mind just wants to jump to the end of the universe kind of thing. But
what if they do that and then they can never come back because they're frozen?
True.
This
Well,
is something to consider.
we
I'm
don't-
sure
we
they
don't
would
know.
sign a
It's-
waiver or
it's
something,
very
get a
confusing.
permission
I
slip.
know waiver.
But yeah, I mean, to bring it back, like dark energy itself is still just such an interesting concept. I think
Right.
partly because it's still widely unknown, and
Right.
it still delves in the theory of just being in theory.
Mhm.
Like, we are still postulating. There's a lot that we don't know. There's a lot that we can come up with to maybe justify, just like Einstein came up with cosmological constant. Like
Mhm.
there's still a lot we don't really know, but I think it's really interesting and it's exciting to see like what might happen in the future, what discoveries we make. So
And one of the truly crazy things is that the difference in force between the strong nuclear force, which is the force that acts over very short distances in atoms, and the force of gravity is about 10 to the 40, which is so huge that Dirac thought that there was probably a mistake because it was just so ugly that it was the fact that it was so that we have such a big difference was just not possible. And that leads us to like a little bit of a crazy thought that we might just be explaining the universe in it completely wrong, and that we might just be
Yes.
confusing all of these things.
Right.
But nonetheless, we have this problem of dark energy, and we can focus our energy on it. And hopefully, and maybe one day, we'll find some really cool answers about where we're going.
it could explain a lot more about other physics. I think that's an interesting take that we could look at it. But I think that does it for us for this episode.
Yep.
Thanks for checking it out, guys. Make sure to subscribe, like the video, check out our social medias, and we'll see you guys next week.
Peace.
Laters.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.